Hi folks, so today we are going to solve 4 problems in the kinetic theory of gases. So here is the first problem. Take a look at the problem. You might want to pause the video and I'm going to give you the solution now. Since the helium is at a higher temperature, heat will flow from helium to nitrogen. Now this process happens where the nitrogen is at constant volume, helium is also at constant volume, so there's no work done, which means the heat supplied is equal to the change in the internal energy. So heat lost by helium equal to heat gained by nitrogen becomes change in the internal energy of the nitrogen should be equal to decrease in the internal energy of helium, which is minus the change of helium. I hope you understand the minus sign. Let me give you a very quick explanation. If I have 100 rupees in the bank and it becomes 95 rupees, the change in the money is minus 5 rupees, but the decrease in the money is 5 rupees. So decrease is minus of change. Let's say the final temperature is T. So what is the change in the internal energy? It's going to be NCV delta T. That is our formula, NCV delta T for change in the internal energy. So for nitrogen, it's going to be 1 mole times CV for nitrogen. It's a diatomic gas, which means CV is 5 by 2 R times change in the temperature T minus T naught. That's equal to minus delta U for helium. Delta U for helium is N, which is 1 mole, times CV for helium. Helium is a monatomic gas, so it's going to be 3 by 2 R times delta T, T minus initial temperature 7 by 3 T naught. There's your equation. R cancels, so it becomes a very simple equation. 5 by 2 T minus T naught is equal to minus 3 by 2 times T minus 7 by 3 T naught. Solving for T, we get T is equal to 3 by 2 T naught. That's your answer. Here is our second problem. If you want, pause the video here. And now I'm going to give you the solution. Now, gamma for the mixture is equal to Cp for the mixture divided by Cv for the mixture. So how do we find Cp and Cv for a mixture of two gases? Well, let's first do Cv. That means we keep the volume constant. And in this volume, we got 3 moles of methane and 2 moles of helium. Now, if you look at the two gases, the volume of helium is the entire volume. The volume of methane is also the same entire volume. Now, when you supply some heat, the change in the temperature is going to be the same for both. Since this is happening at constant volume, there is no work done. So the heat supplied is equal to the change in the internal energy. It's going to be NCV delta T. So it's going to be 3 NCV for methane is going to be 6 degrees of freedom, 3 translational, 3 rotational. We ignore vibration. So that is 6 times half kT. That is 3 kT. So this is going to be 3R is CV times delta T. That's the amount of heat that methane absorbs, plus the amount of heat that helium absorbs is 2 moles going to be, helium is monatomic, so that's going to be 3 by 2 R times delta T. That's going to be N, totally we have 5 moles, and Cv for the mixture times delta T. So we solve this for Cv and we get Cv is equal to 9R plus 3R by 5, and that is equal to 12 by 5 times R. Now let's do Cp. Let's put this answer here, Cv. Now how do we find Cp for the mixture? So imagine that both the gases are contained in a cylinder and we keep the weights on the cylinder fixed. As we supply heat, the gases expand, but the weight remains the same, so the process happens under constant pressure. Both gases absorb heat. How much heat does methane absorb? N Cp delta T. What is Cp going to be? It's going to be methane is polyatomic, Cv is 3R, Cp is 4R times delta T. That's the amount of heat absorbed by methane plus the amount of heat absorbed by helium is going to be 2 times. Cv for helium, monatomic gas, is 3 by 2R. Cp is 5 by 2R times delta T. That is equal to total number of moles 5 multiplied by the effective Cp for the mixture times delta T. So solve this for Cp, we get 17 by 5 R. And so gamma for the mixture is going to be 17 by 5 R divided by 12 by 5 R. So the answer is 17 by 12. Now take a look at problem number 3. So we have capital N moles of diatomic gas, and when heat is supplied, small n moles of it get converted into monatomic gas. So when small n moles becomes from diatomic to monatomic, it becomes 2n moles of monatomic gas. So what was first n moles of diatomic becomes n minus n moles of diatomic plus 2n moles of monatomic. What is the change in the kinetic energy of the gas? What is the total internal energy, the kinetic energy of n moles of a diatomic gas? It's going to be n Cv for diatomic, which is 5 by 2R times T. That is the internal energy, the total kinetic energy. That becomes n minus n times 5 by 2R times T. Remember, the temperature remains constant, plus 2n times monatomic, which is 3 by 2 R T. So the question is, what is the change in the total kinetic energy of the gas? So from the final, you subtract the initial, we find that the total change in the kinetic energy is going to be equal to half nRT. So we come to the fourth problem. Now here we don't even have a gas. We have solid aluminum at room temperature, and the question is, using the equipartition of energy, find the specific heat in joules per Kelvin per kilogram. The atomic weight of aluminum is given. Now in a solid, each atom is free to vibrate in 3 directions. So that means there are 3 vibrational degrees of freedom. This is not translation, because when this is vibrating, the bonds between the atoms are stretching and compressing. So this is vibrational degrees of freedom. And remember, per vibrational degree of freedom, we have to give not half kT but kT. So 3 kT is the amount of vibrational energy per atom, multiplied by Avogadro number will be per mole. So this is the amount of energy which is equal to 3 RT. That's the amount of internal energy in 27 grams, that is 1 mole of aluminum. Now we want it per kilogram. So 1000 grams divided by 27 multiplied by 3 RT gives us the total internal energy per kilogram. Now we want the specific heat. Now that means we are supplying heat to the aluminum. We are assuming that as a solid, it expands very little, and the amount of work it does against the outside atmosphere is negligible. So all the heat goes into changing the internal energy. So dQ is equal to du. Now specific heat here is the heat supplied per kilogram per unit change in temperature. That becomes change in the internal energy per kilogram per degree Kelvin. That means this is the amount of internal energy per kilogram. So differentiate it with respect to the temperature. It becomes 1000 by 27 multiplied by 3R. That is our specific heat. This turns out to be 922.2 joules per kilogram per Kelvin. Well, that's it, folks. 4 problems. I'll see you in the next video. Bye-bye.